Hello students, in this video we are going to learn similarity of matrices, or we can say that diagonalization of a matrix. This is very important concept we have to understand. What is meant by similarity of matrices? Two matrices A and B are considered similar if there exists an invertible matrix M such that M inverse AM is equal to B here. We are talking about the matrix A and B, and there exists one matrix M which is invertible, means whose determinant is not equal to 0 and its inverse exists. Okay, so we are going to call it as an invertible matrix. So A and B are similar if there exists a matrix M such that M inverse AM is equal to B here. So A and B are matrices being compared here. M is the invertible matrix, often called the model matrix. M inverse denote the inverse of M. Now we will see one of the important concept which is going to help whether the matrix is diagonalizable or non-diagonalizable. Means if M inverse AM is equal to some, D is a diagonal matrix, then we can say that this matrix A is diagonalizable. If we are able to express this given matrix A with the help of some M inverse AM is equal to D. Okay, and the many properties are there which are similar for A and D. We will see in detail. So for this, we require the concept of algebraic multiplicity. What is mean by algebraic multiplicity? Suppose they have given the matrix A, then this is a square matrix, and then we can find its eigenvalues. And suppose eigenvalues are denoted by lambda 1, lambda 2, and lambda 3. Then we have seen in the previous videos also, these eigenvalues may be repeated or may not be repeated. Okay, they are distinct also. Here lambda 1, lambda 2, lambda 3 all are distinct. Here lambda 1 and lambda 2 are repeated and lambda 3 is distinct. So these are the few situations may arise. Okay, so from this, how algebraic multiplicity is defined, you can see here. And algebraic multiplicity counts the number of times an algebraic eigenvalue appears. Okay, it means that if suppose eigenvalues are 1, 2, and 3, so 1 has appeared only once. So algebraic multiplicity of this 1 is 1. 2 is a single which is non-repeated, so its algebraic multiplicity is 1. 3 is an eigenvalue which is not repeated, this is a single, so its algebraic multiplicity is also 1. It means like that. And what is meant by geometric multiplicity? Geometric multiplicity counts the number of linearly independent eigenvectors, remember. Linearly independent eigenvectors associated with that eigenvalue. Means suppose lambda is equal to suppose 2, 2 and 5 are there. These are the eigenvalues. So 2 and 2 is repeated 2 times. So algebraic multiplicity of this lambda equal to 2 is 2. And suppose for lambda equal to 2, sometimes we may get 2 distinct eigenvectors, linearly independent eigenvectors, then the geometric multiplicity is also 2. And sometimes if we get only one eigenvector, which is x2, then its geometric multiplicity is 1. Okay, so geometric multiplicity is always associated with the number of linearly independent eigenvectors associated with that eigenvalue. Okay, now let us see one of the important theorem here. So theorem says that if, all of you see here, if the necessary and sufficient condition for a square matrix to be similar to a diagonal matrix is that the geometric multiplicity of each of eigenvalues coincides with the algebraic multiplicity. It means that if AM equal to GM for all lambdas, if AM must be coincide with the GM for all lambdas, if this is true, or if this holds, then you can say that your matrix, which is matrix A, you can express into a diagonal matrix D. And if it is expressed, how this M and D be written, as we will see in this slide. Okay, now a square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. These are the some results. A square matrix A is said to be diagonalizable if there exists an invertible matrix M such that M inverse AM is equal to D, where M is the model matrix whose columns, this is remember, whose columns are eigenvectors of A. So M is a model matrix whose columns x1, x2, x3, these are the eigenvectors of A. And D is the diagonal matrix whose diagonal elements are eigenvalues of A. So D we can write lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. These are the eigenvalues of A, and x1, x2, x3 are eigenvectors associated with this lambda 1, lambda 2, lambda 3. So in this way we can write M and D. See some standard theorems. If A is similar to B and B is similar to C, then we can say that A is similar to C. If A and B are similar matrices, then their determinants are always equal. Next theorem says that if A is similar to B, then A square is similar to B squared. If A and B are two similar matrices, then they have the same eigenvalues. Let us see the condition of diagonalizability. A square matrix A is said to be diagonalizable if and only if for each distinct eigenvalue A, the algebraic multiplicity AM of lambda is equal to its geometric multiplicity. This is the well-known, if eigenvalues are distinct, then AM is equal to GM always, and A is always diagonalizable. And there is one more condition that we will discuss in the next in any other video, that the sum of the algebraic multiplicities of all eigenvalues is equal to the dimensions of the matrix. Now what are the points, what are the summary points that you have to remember? So important points to remember about diagonalization of a square matrix. First point is, if all eigenvalues of A are distinct, then A is diagonalizable surely. Second point, if eigenvalues of A is repeated, then A may be diagonalizable or A may not be diagonalizable. This is the second important point. If eigenvalues are repeated, then A may be diagonalizable or A may not be diagonalizable. Third point, if algebraic multiplicity and geometric multiplicity of repeated value are equal, then definitely A is diagonalizable. And the last point, if the algebraic multiplicity and geometric multiplicity of a repeated eigenvalue are not equal, then A is non-diagonalizable. So thank you. Actual examples we will see in the next video. Thank you very much.